Okay, fluid is anything that can flow. Both liquids and gases are called fluids. The first formula that you come across is density is mass by volume. And density must always be in kilogram per meter cube. Obviously, mass is in kilogram, volume is in meter cube. Second one, pressure is force by area. Right? Unit of pressure, pascals. What about the pressure exerted by a liquid or a fluid? But that's the unit of pressure, that's the unit of density. Pressure by a liquid or a fluid is H rho G. H is the height or the depth, density and acceleration due to gravity. Absolute pressure is the sum of the atmospheric pressure and the gauge pressure. So P is absolute pressure, PO is atmospheric, PG is gauge pressure. Atmospheric pressure, good thing if you know it, 1.013 times 10 to the 5 pascals. If it's not given, then you can use 10 to the 5. So you have to know that. Atmospheric pressure is 10 to the 5 pascals. The next formula is Pascal's principle, where we talk about a hydraulic lift, where you could apply a small force and translate that into a bigger force. F out by Fn is A out by An. That's one set of equations on fluids. Buoyant force. Buoyant force is the weight of fluid displaced. Is the weight of fluid displaced given by the formula density of the fluid times volume times acceleration due to gravity. And equation of continuity is when you talk about liquid flowing through a tube of non-uniform cross-section, right? And then you know that the volume that flows every second is given by that formula, A1V1 is equal to A2V2. That also gives you the formula for volume flowing per second. Please take note of that. Volume flowing per second is given by either A1V1 or A2V2. Then, very important, Bernoulli's principle. It has three components. The first one is the pressure energy, the second is the kinetic energy, and the third one is potential energy. And that should be a constant. Isn't that what it means? Okay, constant. But if you're talking about a tube that is horizontal, then you know that the potential energy is the same on both sides. So you need not consider the third term. So then you can leave out that term and only focus on the other two. Usually, you'll only be asked problems about horizontal pipes. That is Bernoulli's principle. Okay, that's the end of that chapter. Oscillations. You begin with force is equal to minus kx, where k is the spring constant or the force constant. X is the extension or compression. And of course, F is the force applied. Isn't it? Then, the general equation for simple harmonic motion. If you can represent the motion of any object using this equation, then you know that it is simple harmonic. What are the terms there? d squared x by dt squared is acceleration. You can make that out. So if you swing this to the other side, you are obviously going to get a formula for acceleration, aren't you? So that is important there. Acceleration is minus k by mass times x. Okay, remember that. Now the solution of that equation, x is a cos omega t plus or minus phi, where the terms x is the displacement at any time t, and x is always measured from the equilibrium position. A is the amplitude, it is the maximum displacement. Omega is equal to 2 pi times f, where f is the linear frequency. And omega is called angular frequency. So again, omega is 2 pi times f, or it could be omega is 2 pi divided by t, where t is the time period. Because obviously t is 1 by f. Phi, don't worry too much about that. That's called the initial phase. Most of the time it will be 0 for you. In the initial phase it will be 0. What are the formulas for velocity? Velocity is omega square root a squared minus x squared. Again, a is the amplitude, x is the displacement. from this equation, you could get a formula for maximum velocity, because when velocity becomes maximum, x needs to be 0. Now, if x is 0 in that equation, surely you get Vmax as a omega. That's maximum velocity. And then, like I told you before, acceleration is, if you take it to the other side, minus omega squared x. And to find the maximum for acceleration, just think about x becoming maximum, which is a. Isn't it? X becomes a, that's a maximum. Okay. Two important formulas for time period. One is for a spring, 2 pi square root mass by spring constant. For the simple pendulum, 2 pi square root L by G. Total mechanical energy. Total mechanical energy is 1/2 K A squared. Again, remember that K is spring constant even in that case, but it can be related to omega. Always remember, omega squared is K divided by the mass. That will come back again. Potential energy. All right, kinetic energy first. 1/2 K A squared minus x squared. Kinetic energy. Potential energy, just 1/2 K x squared. Easy way to remember, if you add these two, you should get the total. If you add the potential and the kinetic energies, as you can see mathematically, the 1/2 kx squared and the negative 1/2 kx squared get cancelled and you will get 1/2 ka squared. Check. So that's the total mechanical energy. The last part of oscillations, that is the next chapter. Thermal physics. That's how you change Celsius into Fahrenheit, and to change Fahrenheit into Celsius. Do remember what? You see the difference in the formulas? Okay, if you forget that, it's going to be tough. Expansion. All objects expand when heated. Change in length is alpha times original length times change in temperature. Similar formula for change in volume, except that it's beta times. What's the relation between beta and alpha? Beta is 3 times alpha. Okay. Gas laws. Boyle's law. Charles' laws, 2 of them. And then finally you combine all of them to get your ideal gas equation. Terms, everybody knows. P is pressure, V is volume, N is the number of moles, R is universal gas constant, T is absolute temperature. If ever confused, make this the golden rule. Always change temperature into Kelvin. Always change. That will work. So that is the beginning of chapter 17. Meter cube. Avogadro number is the number of molecules in 1 mole of any gas. 1 mole of any gas has the Avogadro number, 6.02 times 10 to the 23. Chapter 17, finished. 18. Pressure exerted by a gas is given by 1/3 Nm V bar squared. Okay, 1/3 Nm V bar squared. What is the N there? The N there is the total number of molecules. M is the mass of one molecule. Come on now. And V bar is root mean squared velocity. Second formula there that you see, the line over the K shows it's an average, isn't it? It's the average translational kinetic energy. Average translational kinetic energy is of a molecule is 3/2 kT. What's K there? Too many K's, but that K is Boltzmann's constant. It's not spring constant, please. It's Boltzmann's constant. Boltzmann's constant is R by N A. R by N A. I think I've written that. We'll come to that. Okay, as we go, there are 2 formulas for root mean square velocity. One of them, square root 3p by rho. Top one is pressure, the lower one is density, please. Don't cancel them out. I'll give you a silly formula. And then the next one is root mean square velocity is equal to square root 3RT by the molecular mass. By the molecular mass. Oh, Three important constants of a gas are critical temperature, critical pressure, and critical volume, right? Three important constants. What is so important about those? In order to liquefy a gas, you have to first cool it to a temperature lower than its critical temperature. That is what is very important. Then, as I said before, Boltzmann's constant is R by NA. Good thing to know. Because you have to know R and you have to know Avogadro number. So if you know both of that, you can calculate K to be about 1.38 times 10 to the negative 23. That is 19 now. Heat absorbed or released by a substance is mass times specific heat times change in temperature. But if it's a phase change, Q is mass times latent heat if it's a phase change. When you mix a hot object with a cold object, heat lost by the hot is equal to heat gained by the cold. And then, first law of thermodynamics, change in internal energy is equal to dQ minus dW. Oh. Work done during an isothermal process, nRT, natural log of final volume by initial volume. Okay, isothermal process, so temperature is going to be constant. Number of moles, N. The work done during an adiabatic process, R by gamma minus 1, T1 minus T2. Those are the two formulas for work done in the two processes. Continuing into this chapter, that's the equation for an isothermal change. This is one equation for an adiabatic change, and that's the second one for an adiabatic change. So both of those are for an adiabatic change. So you have one equation for an isothermal, two for adiabatic changes. Now this one we may not have highlighted before. Mayer's relation, Cp minus Cv is equal to R. You know that a gas has two specific heats. Specific heat at constant pressure and specific heat at constant volume. If you take the difference between them for any gas, for 1 mole of any gas, you will always get 8.314. That will be the difference. And then Cp by Cv is equal to gamma, and you need to know for monoatomic it's 1.67, diatomic 1.4, and polyatomic 1.33. Those are the values of gamma. That maybe the third time that I'm repeating this. So, okay, and then, all right, still more to go. Conduction. Quantity of heat conducted through any material is Ka T1 minus T2 by D. Q is the quantity of heat. T is time in seconds. K, again a K. This is thermal conductivity. A is the area of cross section. T1, T2. Difference in temperatures between that thickness, isn't it? D is the thickness. Now another formula for radiation. Quantity of heat radiated, EA sigma T1 raised to 4 minus T2 raised to 4. Terms stand for Q, quantity of heat radiated. Because there are three ways in which heat can be transferred: conduction, convection, and radiation. You don't have a formula for convection. You only have conduction and radiation. Again, E, the little e there is called emissivity, isn't it? And for a perfectly black object, emissivity is 1. For a brilliant, shiny, white object, it's 0. So E takes values between 0 and 1. Sigma is Stephan's constant, 5.67 times 10 to the negative 8. Watt meters raised to minus 2, Kelvin raised to minus 4. A is the area of cross section. T1 is the temperature of the object that is radiating heat. T2 is the temperature of its surroundings. So if a problem does not talk about its surroundings, you just get rid of that term. That means for you that term would be 0 if it doesn't talk about the surroundings. Last chapter, 20. All right. That equation for efficiency, work over QH will work, that equation will work for any kind of engine. Anything, not necessarily a Carnot's engine. But the equation, not that one, the next one, in terms of temperature, this will only work for an ideal Carnot's engine. Please keep that in mind. This equation will only work if it says it's a Carnot's engine. But the first one, and even the second, will work for any kind of. That means it will work for a practical engine also. That's why. And a gasoline engine or a diesel engine, it will work. But not the last one. Refrigerator, you know that a refrigerator is exactly the opposite of a heat engine. It absorbs heat from the cold object, work is done on the working substance, and it rejects heat to the hot object. So the formulas change. It's no longer called efficiency, it's called the coefficient of performance, isn't it? And you can see that it's QL by W and COP. Again, all the formulas are reversed. Those are the three formulas for a refrigerator. Why isn't it called efficiency? Because these numbers may be more than 1 or more than 100%. But when it comes to a heat pump, the thing that we use in winter to keep ourselves warm at home, there you need to remember that the formula, the first one, instead of QL, it's going to be QH. There you go. That's the difference, QH. So that's for a heat pump. And QH by this. So you have TH minus, TH by TH minus TL. That's for a heat pump. Finally, the change in entropy is dQ by T. Change in entropy is dQ by T. That equation looks very simple, but remember that dQ could be mc delta T, or it could be mass times latent heat, right? And also remember that the temperature there could be an average temperature if you're mixing hot with cold. So that is